7.3 Applications of the normal distribution. So let's do a few application type problems. So here's example number 1. Investment returns. So the annual return from a particular mutual fund is believed to be normally distributed. So Erin is considering investing in this mutual fund. She obtained a sample of 20 years of historic returns, which are listed in the table shown. So you can see all the interest rates, the returns on the investment for 20 years. Most are positive, and there's 1 year that's negative over here. So part A, determine the mean and standard deviation of the data. So this is a sample. So we're going to use sample mean and standard deviation. So the mean value here, if I took all of these percentages for the 20 years and I added them up and I divided them by 20 because there are 20, I will get a mean sample of x bar. The addition of all the interest rates is equal to 248.7. So that's what I will write here, 248.7 divided by 20. And that gives us a mean value of 12.435%. The standard deviation, similarly, if I follow the formula, it's going to be x squared. So if I add up all these return percentages and I square them, so that would give me 4,805.37. Rather, I mistaken my wording. I should say when you square all the return percentages and then you add them together, that's what you get, 4,805.37. And I subtract the n value, which is 20 years of returns here, and the mean value squared is 12.435 bracket squared. Everything is divided by n minus 1, and n minus 1 would be 19. And you take everything and you square root everything. The final result for the standard deviation is 9.49. So pretty simple. You just apply the formulas that you're given and find the mean value and standard deviation. Part B, assuming the data are normally distributed, what is the probability that an annual return will be at least 9%? So to find the probability for at least 9%, I need the z-score. So the z-score is equal to 9 minus the mean value, 12.435, divided by 9.49, which is our standard deviation, and that gives us a z-score value of negative 0.36. So the probability that the interest rate or the annual return will be greater than 9 is equal to the probability that the z-score is going to be at negative 0.36. So if I go to a z-score table and I find negative 0.36, so here's negative 0.3 in this row. The column determines the second decimal place, so 0.06 is over here. So finding the intersection of the two gives me a probability value of 0.3594. So 0.3594, that one right there. So remember, this 0.3594 represents the probability that z is less than negative 0.36. So it's 0.3594. So if I was interested in the probability of z being greater than negative 0.36, which is the same thing as saying x is greater than or equal to 9, then I have to do the indirect method. So 1 minus 0.3594, which would be approximately equal to 0.64 or 64%. Okay. Now, what's the probability that the annual return will be negative? So what's the probability that p of x less than 0? Well, that's going to be equal to, I can write also the z-score this way. So the probability of the z for a standardized normal distribution, probability of z being 0 minus less than 0 minus 12.435 divided by 9.49. So this is just another fancy way of saying here's my z-score. What's the probability of z being less than that z-score? Okay, so in other words, what's the probability that z is less than, if I evaluate all this, is less than negative 1.31. So I go to a z-score table, look for negative 1.31. So here is negative 1.3. The second decimal place is 1, so there is 1. So the probability is 0.0951. So 09, let's try 0951. So 0951. There we go. So approximately 10%. So a 10% chance of a negative return. Okay. Part C, out of the next 10 years, how many years should Aaron expect to show returns of 6% or more? What assumptions are necessary to answer this question? So, 6% or more. So what's the probability? The question is, what is the probability that the rate of return x is greater than 6? Okay, so for this, I need to calculate a couple of z-scores here. So I need to know, or rather just one z-score. So let's convert this to a z-score. So in other words, I'm looking for the probability that z is greater than 6 minus the mean value, 12.435, divided by the sigma, or standard deviation, 9.49. And so that's going to be equivalent to the probability that z is greater than negative 0.678. So all of this resolves to negative 0.678. So let's look at the z-score table once more. So negative 0.6, here's negative 0.6. And let's, we only go to two decimal places here, so 0.7 is the next one. It's going to be 2.254. Alternatively, I could round to 0.8, 0.08 rather, or 0.68, and I can get 0.2483. So it's going to be somewhere in between these two. I'm going to just say 0.25. So it's a nice number in between them, so 0.25. So the probability and so remember, this is question is greater than, right? So what I just read, the 0.25, the value between these two values right here, that 0.25 represents the probability that z is less than negative 0.6. So if I write that down here, the probability that z is less than negative 0.678 is equal to 0. I kind of got the number already. It's 0.25. Yeah, 0.25. So 0.25. Yeah, okay. So that's the probability for that one. And so the probability that z is greater than negative 0.678 would then be, by the indirect method, 1 minus 0.25, which is equal to 0.75. So what does that mean? It means that there is a 75% probability of a return greater than 6%. So you can say the expectation is about 7 to 8 years out of the 10 years of investment that Aaron would get greater than 6% in returns. And I say 7 or 8 years because 75% of 10 years is 7 to 8 years. Okay, example number 2. Suppose the birth mass rather of a breed of guinea pig follows a normal distribution with a mean value of 100 grams and a standard deviation of 10 grams. I'm just writing down the interpretation of these numbers. The mu value is 100 grams, Standard deviation sigma is 10 grams. And we're assuming populations here rather than a sample. So part A, what is the probability that a birth mass from a large sample lies within 1 standard deviation of the mean? So Z is going to be equal plus or minus 1. So what's the probability that Z is between -1 and 1? Well, that's really what the question's asking. 1 standard deviation from the mean value. So I'm looking for the probability of Z being less than or equal to 1 minus the probability of Z less than or equal to -1. Okay, because again, think about the graph. Here's a standard deviation. Here's your mean value. Z positive 1 over here, Z -1 over here. So Z equals 1, Z equals -1. So if I find the probability that Z is less than or equal to 1, then I'm looking for, that's giving me the area of this portion of the graph. Okay? But then if I subtract the probability that Z is less than or equal to -1, then I get to subtract this portion of the graph, leaving me with what I really want is the portion between -1 and +1. Okay, so that's what we're doing here, and that's how I'm setting up the formula. So if I look at the z-score table for 1, so here at 1, it's 0.1587. Oh, sorry, that's -1. So 1 is +1. Where's +1? Over here. 0.8413. And for -1, it is 0.1587. So I just want to subtract those two values. So I'm going to subtract 0.8413 minus 0.1587. And that's going to equal 0.6826. All right, so question number 2. What if the sample is 2 standard deviations of the mean? What's the probability that the birth mass from the large sample lies within 2 standard deviations of the mean? So Z is going to be plus or minus 2 standard deviations. So the probability I'm looking for is the probability that Z is between -2 and +2. So that's going to equal probability that Z is less than or equal to 2 minus the probability that Z is less than or equal to -2. So if I go to the z-score table for this one, at +2 I have 0.9772. For -2 I have 0.0228. I'm going to subtract those two values. So 0.9772 minus 0.228, and together that makes -0.9544. So there's a 95% chance that the birth mass from the sample is between -2 and 2, or 2 standard deviations from the mean, and there's only a 68% chance that the sample birth mass is within 1 standard deviation of the mean value. So part B, does the answer in part A depend on the mean and standard deviation of the distribution? No, it does not. Okay, so 1 standard deviation from the mean always results in a z-score of -1 or 1. So no, 1 standard deviation from the mean always results in a z-score of -1 or 1. And on the standardized normal distribution, the mean values is automatically 0. So the actual distribution, the mean and standard deviation of the distribution of this will not matter at all, because we're using the z-score of 1 and over here 2 to help us find the probability. Okay, example number 3, manufacturing. Precision racing pistons for a high-performance automobile engine need to have a diameter of 5 inches, accurate to within 0.0001 inches. parts manufacturing company would like 95% of its pistons to fall within this range. What standard deviation is needed to meet this requirement? So let's look at what is our z-score. So our z-score is going to be composed of our standard deviation and some x value minus the mean value. The mean value is 5. Okay, so we're going to calculate the upper limit. So the upper limit of our z-score has to reflect the fact that this automobile engine piston must be within 5 inches accurate within 0.0001. So it has to be at most 5.0001. Otherwise, it won't work. So 5.0001 will be my x value minus 5, the mean value, divided by sigma. The lower limit, same idea, but subtract. So it's going to be 4.9999, or 4 nines, minus 5 divided by sigma. Okay, so if you want 95% of your pistons to fall within the range, so you want, here's normal distribution, here's your normal distribution, you want 95%, so it has to be within some range, this has to be 95%, right? This whole thing right here. So what will your limits be? That's an interesting question. Think about the normal distribution, right? Even on your z table, the notes from the previous lesson. Let's go to those for a moment. So over here, what interval would represent 95%? Well, that's going to be 2 sigmas above and 2 sigmas below the mean. So the z-score has to be 2. Okay, so let's go back to our thing here. So the z-score, so for 95%, of all pistons, the z-score must be plus or minus 2. Okay, so if the z-score is going to be 2, then sigma is going to be, so plug in 2 for your z-score, 5.001 minus 5 divided by sigma. And so sigma, when I solve for sigma, is going to be 0.00005 inches. So your piston cannot deviate more than 0.00005 inches. That's your standard deviation. And that ends the several examples we're doing for section 7.3.